I'm Paul Lewis, and to start the program today, I want to introduce the Interim Dean of the College of Agriculture, Natural Resources, and Design. That's for all of you. To me, it's still the Ag School, okay? And so, currently serving as Interim Dean is Dr. Ken Blemmings. And Dr. Blemmings was a member of the faculty in Animal Nutritional Sciences, where he rose to the rank of Professor of Nutritional Biochemistry. And for the last 5 years, he's been serving as the Dean of the Honors College for the university. And he's just recently been appointed as the Interim Dean for our college, and we're delighted with that appointment. And so I would only tell you that if there's things about it that you think are great, you tell all of that to Dr. Blemmings. If you've got complaints, you give that to Matt Wilson or Paul Lewis. We'll handle those. And so with that, Professor Blemmings, I'll turn this mic over to you.
Hello, everybody. Glad to be here with you this morning, and thanks for coming to the Appalachian Grazing Conference. And it's my great pleasure to introduce our first speaker, and that is Dr. Jason Hubbart. Dr. Hubbart is the director of the Institute of Water Science and Security at WVU, and a member of the faculty in plant soil science and a joint appointment in forestry as well. And he will be talking about improving animal efficiency and water quality systems, a sustainable agricultural model farm. Dr. Hubbart.
Thank you, Dean Blemmings. Hello, everyone. Have you ever listened to a hydrologist speak before? Okay, I get a lot of smiles out there, so why, that's like one of the major ironies of being a hydrologist, that we're also some of the driest speakers in the world. And why they would do that right at this afternoon snooze hour. I think it's some kind of hazing. Welcome, everyone. Great pleasure. What a great pleasure it is to be here today. Appreciate you being here for this talk. The title is a lot to think about. I will admit that it's an aspirational title, but unless you know where you're going, you hardly ever get there, right? And I was asked to talk about environmental water quality, so I'm going to do that for at least one slide. And then talk to a bunch of things that are connected to that idea. So I also want to just take a moment to appreciate the fact that we partner with so many really great colleagues in our state and agencies, and so many of you are here today, and just how really important those relationships are for the Davis College. Those relationships have carried forward literally for decades and decades, and are critical to what we do, critical to our land grant mission, but also critical. That relationship is important for you, and we understand that, and we don't take advantage of that, and we're just so pleased to have the partnerships that we do. Also wanted to shout out to our NRCS colleagues that are here today as well. And in fact, I point to them often for obvious reasons. Some of this talk is focused around some work that we're starting out in Wardensville. I'm going to speak more on that in a few minutes. But just how important our NRCS relationships are, and those also date back decades, literally decades. Those are long-lasting relationships. We have a number of current projects with NRCS. We have just recently In collaboration, we have a new Chesapeake Bay Watershed Science Advisor, Dr. Elliot Kellner, who's going to speak directly after me. We have this new objective plan for Wardensville Farm, which I'll speak on soon.
Oh, thanks.
We have collaborations through the Davis College Natural Resource Analysis Center, collaborations with the WVU Health Sciences group. Those are all in collaboration with the NRCS. But not to avoid or I need to be sure to mention our other colleagues and other agencies that we do so much with, and I'll mention more of them towards the end of the talk. Ultimately, nothing transformative truly occurs in isolation. We embrace, nurture, and greatly value our state and Fed agency relationships, as well as our interinstitutional relationships. It's all really important to everything that we do. Okay, so I'm going to focus the talk on, I'm going to do an unabashed kind of intro to the Institute of Water Security and Science. It's important. Just mention briefly what we do in the Institute. Talk very briefly about environmental water quality. I was asked to speak on that, so I'm going to spend a little bit of time talking about what that is and some issues related to it. Challenges in agriculture, new approaches in science-based management, and what we're learning. All right, so the IWSS, our mission is to develop sustainable solutions addressing contemporary water quality, quantity, management, and use problems while strengthening West Virginia's water security and environmental, economic, social, and cultural well-being, and broadening West Virginia University's water stewardship impact and prominence nationally and globally, and I think that was all one sentence. That's a lot. I want to also mention that the university realized many years ago that water is an incredibly important commodity for our state, for obvious reasons. West Virginia is a headwater state, and we have lots of water, and we are stewards of our environment, and water is part of that. And in that recognition, the university realized that's a place that we should develop further, continue to grow, and see what we can do to expand interdisciplinary, integrative type research across the campus, but as well as throughout the state. There's a lot to do with water resources all the time. So a little bit, again, about the background. We were created to coordinate and promote research in various areas related to water, including, but certainly not limited to stewardship, agriculture, energy, resource management, innovations in water management, policy, human health, land use practices, sustainability, and other emergent areas. We promote all activities that improve water resource awareness, management, and security. Water is the great integrator. Everybody in this room cares about water. Even if all you do is drink it, you probably care a lot about it. At least 70% of your body is made up of it. So it's pretty important stuff. It is, again, it's the great integrator. It brings us all together. It's a common ground. So our more than 300, I should say, the Institute started on January 1st of 2016. We are new. And yet we already have over 300 faculty, researchers, industry, agency, partner institutions, and other affiliates. We feel pretty good about that. That's great progress, we think. Our affiliates identify key needs and innovations in water resources. They design and develop new techniques and methods. They validate best practices that advance science, stewardship, policy, and human health. They broaden and outreach and service to state and federal agencies, landowners, and managers, and foster broad integrated interdisciplinary participation. And ultimately, and probably one of the most important things that we do, is we help train tomorrow's professionals. So here's how you get a hold of us. I'm not going to hover here too long. There'll be a PDF available, which I've already forwarded you, Paul. And so perhaps that can be shipped around. Otherwise, Google us. That's the answer for everything. So again, I was asked to talk about environmental water quality. So what is it? That's a good place to start. And so it's also called ambient water quality. Ambient meaning what is the current status, essentially. What is it right now? And the kicker about that is that the question could be more specific. What is it? What is water quality or the water situation right now where you are at? And that changes spatially and temporally. So this relates broadly to lakes, streams, rivers, and oceans. It's broadly surface waters, though it does and can extend to the subsurface through subsurface and surface interactions. So it definitely reaches into groundwater supplies. And water quality standards vary significantly. One size does not fit all, even though we've tried to take that approach for a long time. It's definitely within the last decade or so that we've come to increasingly embrace the reality, which is one size doesn't fit all, and that what we learn in one place may or may not apply very well in another, and that those locations could be relatively close. Nowhere is this more true than in West Virginia, where we have such amazing variability in terms of the landscape and topography and so on. So there are physiographic differences, physical process differences, biological and ecological process differences, and differences in terms of how we think about land use practices. So in other words, the desired human uses vary very much spatially. Well, we've learned a lot. So I decided to kind of spin this talk a little bit broadly and base that on some of my ongoing experiences in the Midwest as well as here. So the Chesapeake Bay program, which started in the mid-1980s, I'm the West Virginia gubernatorial appointee to the Chesapeake Bay Science and Technical Advisory Committee. So that provides an opportunity to really understand the state of the science in Chesapeake Bay. It's been an outstanding opportunity for me to network and get to know colleagues, state fed agencies, and so on throughout the watershed. Really, really important relationships and many, many advancements in terms of how we manage agricultural landscapes as well as other mixed-use landscapes. And then the Mississippi River Basin, of course, they have the Gulf Epoxy program that was established around 1990, developed much further by the mid to late 90s. I happen to remain a member of the Southeastern Regional Association of the Gulf Epoxy Task Force that allows me to keep a foot in the Mississippi River Basin and in the Midwest. And as it happens, this is important for West Virginia, I think, because as it happens, about 2/3 of West Virginia is in the Mississippi River Basin, and about 1/3 of it is in the Chesapeake Bay watershed. So we quite literally straddle them. And my thinking is that we have an opportunity to start thinking about integrations between those programs. I'll get back to that in a minute. So we have many common environmental water quality challenges. And I tell my colleagues in the Chesapeake Bay program, as well as in the Gulf Epoxy group, that we have these commonalities and they're still having a difficult time believing it. But I'll get back more to that in a second. In the MRB, there are 31 states. In the Chesapeake Bay watershed, there are 6 states plus the District of Columbia. This is, it's easy math. This is a vast majority of the lower 48, vast majority of the United States. And we have learned a lot. And these have been ongoing, long-term projects to look at, essentially, agricultural practices and, of course, nutrients. One of our common environmental water quality challenges, then, is hypoxia. So this is the decomposition of organic material or excessive supply of nutrients that lead to algal blooms. And, of course, increased primary production. Eventually, those algae die, and they settle to the bottom and decompose. And that process requires oxygen. That oxygen is depleted and it creates dead zones, i.e. places, areas, vast air regions of water that have very low oxygen content, and organisms that are in those waters, unless they can swim away, will perish. This is a big deal. It affects fishing industries and many, many livelihoods as well as food supplies. So that's a common problem, Chesapeake Bay watershed, as well as the Mississippi River Basin. So how do we control it? Well, we need to control nutrients. This is not new information to you. We need to control those nutrients, and we need to control sediment flux. Well, we know that nutrients absorb to and are carried along or transported by sediment, so that seems reasonable. And we need to be better about how we manage the landscape. So these are all things that we've been working on for a very long time. And there are many, many advancements in terms of how we manage these things. It's more complicated though. I'm going to get into some of the complications of this process. To manage water, for example, which by the way happens to be the transport mechanism for nutrients and sediment and pollutants, we need to understand the budget, i.e. the water balance. So where does the water come from? Where does it go? It sounds simple, it's really complicated, especially if you have a watershed, if you live in a watershed, which I think probably most of you do. If you don't live in a watershed, raise your hand. But the other is, people want to do different things with their property. You know, you may have a dairy, you may have corn, you may have a parking lot. Those actions, those activities create different balances for how water moves through the environment. So that varies very much, dynamically, spatially, and temporally. So if managing water means that you're best off to figure out the water balance, then maybe to best manage nutrients, we need to understand the nutrient budget as well, i.e. the nutrient balance. Again, where does it come from? Where does it go? What happens to it along the way? Incredibly complicated. So we don't do it. We don't do it quite like that. Why? Because of time, money, labor. It's really expensive. I'm going to get into some of the reasoning behind that. So instead, what we do is we take a reductionist approach. We start to chip away at pieces of this complex problem, which is, again, closing the nutrient balance. We just want to focus on nutrients for now. So we'll split this equation, this complexity, into multiple places. I'm just going to supply a few examples. There are plenty others. So we'll consider the physical hydrology and soil physics, or the ag management effects on soil-water dynamics, the hydrodynamics between unsaturated and saturated zones, soil moisture, nutrient use efficiency. We'll think about artificial drainage, form and function effects on hydrologic connection to fields and regional waterways, or management to optimize field conditions and reduce impacts to downstream waters. We'll think about the costs and benefits of field water management and drainage and irrigation costs, in terms of their installation and ongoing maintenance. We'll think about optimizing nutrient efficiencies, uptake efficiencies, and water management associated to that. Surface water management, groundwater resources, public environmental health risks, and agricultural water management. These are reductionist approaches, issues or simple questions that we can wrap our brain around and that we can do something about in what are common budget or funding period cycles, right? And of course, soil health. This is an evolving definition, so that being of soil health, but it's the importance of soil carbon and soil moisture and so on. Also the soil health and human versus natural variation over space and time, and soil health and soil biology. Really complex questions that in and of themselves are difficult to answer, but nonetheless a reductionist approach. You can imagine that we have to address all of those issues and plenty others to be able to start to think about closing a nutrient balance. But if we could do that, and we could close that balance and understand where the nutrients are coming from, where they're going to, when, where, and how, and nutrients also transform as they move across the landscape or down the stream channel. It's all really complicated, but if we could do that, then we would understand where to best manage those pollutants or that runoff. So what's missing? So reductionist approaches are often disconnected. By that I mean we take our reductionist approach and we head out after solving this question, and then we forget by the time it's all done, because it was exhausting and a lot of work to be able to collect the data and disseminate some new information in advanced science and management and all these other things, and we forget to go back to the reason we did it in the first place, which is, again, adding a piece of the puzzle to solving or closing that nutrient balance. And then, of course, what else is missing is communication between groups. And we could qualify the word group any way you want here. I'm just going to qualify it by Chesapeake Bay program and Gulf Epoxia programs. Those folks don't talk much. It's stunning. And yet there's a wealth, massive wealth of knowledge, of understanding. But they don't really talk, and for some reason they think that their problems are different. Now the way they have approached the problems are different. The folks that initiated the processes and programs in those larger programs are different. The funding sources are a little bit different. but the environmental issues are not really. Coupled to that is you have hundreds and hundreds of folks who have based their careers on their reductionist category in those watersheds. That's important, and that should be really important to us, and it requires us to be empathetic to the fact that they have bitten off a chunk of this puzzle and done extremely, very, very good and needed work. And yet we are not connecting the dots here. We need to get back together and communicate. So what else is missing is incentivized sharing of information and collaboration. Somehow we have to incentivize those processes. We have to make it okay, basically, for folks to give up parts of their fiefdom and or share information so that they can establish or create more, do more with the information they've got. And we need long-term fiscal support for ongoing monitoring, communication, and collaboration. That's also a tall order. So the consequence of this is we have a little discussion about changing how we do the science. A little discussion on that. There are very few successful integrated interdisciplinary teams, and we have a lack of dedication to finding common ground to achieve buy-in, to work together to accomplish more. This is very difficult. This is the hard stuff. Working on interdisciplinary teams with a lot of people that think differently about what's important or a priority in the environment or anything else that we do is incredibly challenging. It's very, very difficult. So what do we need to do? We need a new kind of long-term commitment during a time when funding systems and cycles are not always in sync. I was sitting in a recent Chesapeake Bay Science and Technical Advisory meeting, and there was an individual that was there who was his last meeting. He was about to retire, and he said, "We've spent a lifetime collecting broad-scale data. We don't have enough information up in the watersheds. We can't run our models. There's too much variability out there." Well, the world has changed. Global population has doubled in the last 50 years. That's an incredible thing to think about. If you look around once in a while and you say, "How did all this happen so fast?" or "Did I fall asleep?" That's real. Things are changing so fast, we can't keep up with it. So we need to think beyond all of this and somehow start to consider how we're going to work together. There's no way around it. It used to be you could work alone and work in your cottage industry as a faculty or as a researcher or a manager and do your thing and it was okay. Yeah, it's not today anymore. So we need long-term studies, we need large teams, interdisciplinary teams loaded with folks that think differently about the world, and we need adaptive science. We need to be able to learn and change direction and grow with that. Again, this is very difficult. This is the hard stuff. Hence, Raymond Memorial Farm. So a few of us got together within the last few years and realized, wow, we've got this latent or we've got this hidden commodity out in Wardensville, which, as you can tell, is located right up there. We have this great opportunity to work with our farm managers and the labor forces out there to achieve more. The Wardensville Farm, the Raymond Memorial Farm, is known for its bull sale and so much more. But it's an amazing resource in which we could start to think about working towards closing a nutrient budget, because we have basically a potential for a closed system out there. A massive greenhouse, massive outdoor laboratory. And so a few of us have started to work on that equation. So first step is to take off these detriments to that work. And to think about, do we have an opportunity to do something that is so rarely accomplished? I want to be sure to note that other folks have made giant steps towards closing nutrient projects. But very rarely is it occurring at a farm scale, let alone something that's approaching watershed scale. So we have an opportunity to think about approaching those ends, and we're working on it right now. So for example, right now, this spring, we are installing a series of sensors. This is the Wardensville farm, the lower portion of the farm. And all of these funny shaped objects are sensors. So this is what we do as hydrologists, biogeochemists, is we're going to install a whole bunch of gauges and start to monitor stream flow as well as shallow groundwater. We're going to start to work on understanding how water moves back and forth from our surface water supplies to the shallow groundwater supplies. what happens is nutrients and sediment and so on move down the stream channel and eventually to the Kakapan River, which here, and start to work towards closing that budget. The critical part of that, of course, is also feed efficiency, and Matt Wilson or Kevin Schaefer, one or the other, will speak on this in a little while. So it is definitely an integrated, interdisciplinary, super complicated, collaborative project, and we're just getting started, and there are probably a couple dozen people already engaged in the process. This means that we'll need to invite lots of other folks to the table. As soon as we can start collecting these data, we need to start talking to microbial ecologists, folks that understand soil microbes, and other folks that can get us help in biogeochemical cycling. As nutrients transform, of course, in the waterways. Keep moving. So what kind of information will be generated here? So I thought I would, since this is a new study, I thought I would provide an example or a case study of a project that I had in mid-Missouri. So this is the Hinkson Creek Watershed. It's a catchment area of about 231 square kilometers. It was 303 delisted creek in 1998. It's a typical mixed land use watershed. The top half of it is very much forest and ag. So that's up there between sites 4 and 5, as you'll see. So in 2007, we installed 5 gauging sites. So again, it was listed in 1998. By 2007, and that's when I arrived at Mizzou, there was no progress, quite literally. And the question always was to me, how are we going to fix the Hinkson? So we decided to start doing monitoring. This is actually an experimental watershed study design. It's called a scale and nested experimental watershed study design. So everybody living in that watershed became part of my science projects. Our major goals for this were to close the water mass balance, which of course again is the transport mechanism, close the suspended sediment mass balance, and quantify nutrient export or load from the watershed. So it took a few years to collect enough data to be able to really do something. But since 2010, we've published papers on all of these topics. Parenthetic notations are the number of publications. That's important stuff to an academic. So papers about watershed management, suspended sediment, flow dynamics, floodplains and shallow groundwater, precipitation processes, stream water chemistry, watershed modeling and chloride, physical habitat assessments, macroinvertebrates, stream temperature, nutrients, urban heat island issues, legacies and effects. And during that time, we graduated 18 graduate student theses and dissertations, and we worked with a whole lot of other folks in the process. In 2011, we created a collaborative adaptive management program, which included all of these entities. This is an ongoing process, and this is the hard stuff. When we started the collaborative adaptive management program in 2011, we were split into 3 groups: an advisory group, a stakeholders group, and a science group. I was on the science group, go figure. And the first 6 months was just learning how to communicate. It hurt. This is hard for most people. We want to get to work. Let's get some stuff done. This is painful. It was painful. But at some point I had an aha moment, which was, oh, wow. If I really start to listen, and I mean really listen, to what people say and think, and I learn from that and allow myself to grow with that, then we can establish a whole lot. It's really difficult. We live in a complex society and with many contemporary issues that are very, very difficult to grapple with, and this is part of the job these days. We all have to do it. Well, so what are we learning in Hinkson Creek? So I will also say that I stopped the monitoring for that project at the end of 2015 when I moved to West Virginia. We had about 8 years, variously, of different data sets. And all of those papers and topics have allowed the collaborative adaptive management teams to continue to meet, to develop, to adapt to the science. Okay, so we learned this, what are we going to do next? Okay, so we've learned there's this hot spot up in the top 2/3 of the watershed. Maybe we should do something about that. We've got a dump up there that actually seems to be leaking. Maybe we should do something about that. And so this is actually working. It's really exciting. It's fun to be part of. But we've been learning a lot. So a couple things that are kind of fun to think about, depending on your perspective, is this idea of regulatory misdirection. So for example, Hinkson Creek was listed as polluted on the 303D list, literally for unknown reasons. So that took me a while to come to terms with. Maybe I'm not quite there yet. I think it's a good idea to know why you're listing something. But nonetheless, the process was successful because just listing it got that creek, that system attention. 56 kilometers of drainage got it attention. And people started to take notice and realize, hey, this is important to us. Also, this issue of forgotten practices in deforestation or agriculture and mining. Somehow, through the years and years, folks forgot that there was mining. That was weird. We dug that one up, and because we'd never heard a peep about it. But that, of course, mining practices can reroute water, right? It can change how water moves through the landscape. Scientific short-sightedness. We get into our reductionist research, and we can sometimes forget that there's this entire universe of other pieces and parts floating around us. So one thing we learned is that there's different geological material throughout that watershed, which leads to different suspended sediment regimes. We have water displacement through karst and mining. We didn't know where that really was happening. We have this urban versus agricultural nutrient dichotomy, which is that basically at a given time of the year, nutrients are an ag problem. The other time of the year, it's an urban problem. People love to grow grass. That's maybe intuitive, but we were able to quantify it, and that's important. When you can quantify something and show that it's a statistically significant difference, that's important. It says, maybe we should pay attention. So science-based progress, the ability to study design to provide infrastructure to detect. If not for that experimental watershed study, we couldn't have done the work, couldn't have done this. The power of 5 sites in a very large watershed, couldn't have done it without that. The cost. This is interesting. In 2014, we did an assessment. There were over $100 million spent from 1998 to 2008 on that watershed to try to understand what was wrong with the Hinkson. No progress. From 2008 to 15, there was $1.5 million invested, which came through federal grants that I obtained in the Watershed program. And we had many, many discoveries, science-based information to guide policy and decision-making. And this is no longer about delisting. This is important. Waterways get listed, but wouldn't it be interesting if at some point your collaborative, interdisciplinary, differently thinking crews decided that the listing was not really an issue, because even if it was delisted, you're still going to continue to pay as much attention. And you decide that you learn enough through that process that these natural resources are important, regardless of listing or not. So the Raymond Memorial Farm is going to help us to answer the right questions for agriculture in general, and the Chesapeake Bay watershed in particular. We're working very closely with the Chesapeake Bay program, modeling group, and you name it, we're working with them. They are aware of what we are about to undertake in Gordonsville, and they can't wait for field trips. And we are going to be feeding them new data sets and new information, providing that upland information, that higher resolution, high density data that they so desperately need to be able to run their models. So the RMF is also a collaborative springboard to address many of the greatest contemporary agriculture and water resource challenges of our time. This is a high-tech program. It's difficult to do this work. Again, there are many intermingled pieces and parts, and it requires the latest science, the latest understanding to make progress. Again, there's going to be some discussion about feed efficiency and the growth safe system just in a few minutes. It's also an opportunity for contemporary hydrobiogeochemical studies. I'm working with the group in the Chesapeake Bay program right now, looking at nutrient spiraling processes just how nutrients and other pollutants transform as they make their way downstream in aquatic ecosystems is something we just don't understand real well. It's surprising, but there's a lot we still do not understand. And finally, it's a rich collaboration, a teaching and research sustainable farm. And that's a big deal. That's what we do in Davis College. We educate tomorrow's agricultural professionals, natural resource professionals, and we educate them through field experiences, and this is part of that equation. Really, really important. Also, just want to introduce another current watershed study. This is the West Run Watershed, which is just a few miles somewhere, I think, that direction. In Morgantown, it's an area of 26 square kilometers. So after the 230 to 40 square kilometer 5-gauge site project in Missouri, I had a lot more questions, such as the nature of science, job security. So, and one of the things I wanted to do here is find a watershed that had just about everything going on in it, which West Run does. You imagine it has it. Airport, mining, of course, ag, you name it, it's happening there. Shopping malls, I could go on, nonetheless. So we have 22 gauging sites. This is literally a globally unique project. There's nothing like this happening elsewhere on the planet that we are aware of. And why is this important? Because it enables us to take a watershed and look at distinct land use practices and the effects of those practices on water, water quality, water systems, water quantity, and the transport of pollutants from each of those land use types. This is a big deal and it's important, and it's akin to what we're trying to do in Wardensville. Okay, so in synthesis, a few thoughts. Multiple land uses, climate, culture, legacy effects, and many other attributes result in multiple interacting stressors that affect agricultural production and aquatic ecosystem health in contemporary watersheds. Back in the old days, I don't know, 30 years ago, we would have conversations about watersheds that have one land use type in them. It's completely forested, it's completely agricultural. Boy, life was good. And then population boom kept on growing, and it's not that way anymore. We're all living in a mixed land use watershed. It's really complicated stuff. The landscape we manage today is very much a reflection of the past, a reality of the present, and our livelihood for the future. It's critical to invest in comprehensive programs to advance management. We have to do it. In other words, we have to have that greater commitment. We also need to ask the right questions. So what data are needed or necessary? As a hydrologist, a physical hydrologist, and an environmental biophysicist, I'm going to tell you I want more data just about every time. But there are some management, land management questions that we don't need all those data. It might be easier, right? And so we need to be clear about what information we actually need to solve what problems. So and that includes what sorts of accuracy and precision will supply that information. Which stakeholder groups should we ask for collaboration? That's difficult, by the way, because you don't want to exclude anyone, but you still want to get things done. And you want to be, invite folks to the table. But that can complicate things, and so that's part of that difficult territory that makes this such a challenge and an opportunity. How do we want contemporary watersheds to function and support natural resources? This is where things get complicated, for sure. What do we want watersheds to look like in the future? It's a simple question. But you get a bunch of people in a room with a different idea about what that looks like, that conversation will take months or years. We should get started. So what are the obstacles to long-term studies? How can we navigate in the current fiscal environment? I'm asked that question a lot. What I've learned is that you have to figure out a way to not create a project, but to create a program. You have to create a program that's embedded with projects. And then you can leverage those projects as you continue towards the goals of your program. It's complicated, it's a little more work, and certainly takes more thought, right? But it can be done. So, closing comments, WVU and our agency organization partners are meeting contemporary challenges head-on with farm to watershed scale programs. We're advancing land management and improving agricultural practice production with science-based information. And we are committed, we are encouraging and working with greater commitment. And this is resulting in constant discoveries. It's an exciting time. It's a challenging time. But there's so much opportunity and so much to do. Also want to be sure again to shout out to all of our state and Fed agency folks, and many of their logos are here. Thanks for your ongoing collaboration and support, expertise, and everything else that we enjoy with those relationships. And apologies if I've missed anybody, which is possible. And thanks again, Paul, for the opportunity to be here today. Thank you.
Are there any questions for Dr. Hubbart? Well, we've got a minute. If not, I will display my ignorance and ask him to tell me what a 303D is, because I do not know.
303D list, raise your hand if you know what that is. Okay, one needs to know one's audience. 303D list is the EPA listing for waters that are impaired. It's a listing of impaired waters. And that impairment could be in just about anything. Is there any other questions that I can avoid?
Thank you, Dr. Hubbart.